Dr. Muhammad, and this is another video under the Slope-Deflection Method, and I'm going to talk today about the analysis of frames with side sway. Okay, now let's go and recall what we have said before in the previous video. We mentioned that the Slope-Deflection Method can also be used for the analysis of frames because if you remember that we have mentioned it is only convenient for continuous beams, but it can be used for analysis of frames. And I have mentioned about something that is important, which is the concept of the inextensible element, which means that the axial deformations of members are neglected in the analysis, and the members are assumed to be inextensible. They cannot undergo any axial elongation or shortening. Already I have mentioned about this before, and we said that for frames in general, the members that we are dealing with and the materials that is commonly used in engineering practice is going to be inextensible, whether it is RC or steel or any other material that is commonly used in engineering practice. Inextensible means that the axial deformation of the members are neglected in the analysis. Okay. And the third concept that I have mentioned before, that the procedure for the analysis of frames without side sway is almost identical to that for the analysis of continuous beam. Actually here it is, in our case, we are going to talk about with side sway. This slide actually from the previous video, so it is the same. So we are talking here in this video with frames with side sway. Okay, now let's jump directly into the frames with side sway and let's see what is the rationale behind them. If we look to this frame, we are going to judge it as frame with side sway. Why? What is the reason for this? The reason is there is no kind of support at the level CD. If we have a support here, horizontal hinge for example, we could say that it would prevent any lateral movement here. So our frame is free to translate laterally. This is why we can find delta here. This is delta. And in the same time, we are going to find that the point C and point D, they are free to rotate. As you can see, they are free to rotate. So we have theta C and theta D. This means that we are having three different unknowns in our problem. The first unknown is theta C, the second is theta D, and the third is delta. Okay. Well, these are the three main unknowns that we have here. You might ask me, but still we do not know the moment at A, the moment at B, the moment at C, the moment at D, right? We do not know all of them. The answer that all of these moments are going to be defined in terms of these three main unknowns when we apply the slope deflection method at each point. Okay? Then the slope deflection method equation requires the chord rotation. Do you remember the chord rotation? Which is the rotation between the dashed line that is connecting between the start and the end of the member and the vertical if we are talking about columns. Okay, so this means that we are going to have psi AC and psi BD. Okay, so this is the three main unknowns based on which we are going to design, or based on which we are going to obtain all the moments at each point in this frame. By the way, this psi AC, it is easy to be obtained. This is tan of this psi AC, okay, it equals to delta over the height, which is h. So still this psi is going to be defined using one of our unknowns, which is delta. Okay? Okay, now let's jump into the equations directly and let us see what we are going to do. We are going to apply the slope deflection equations for the three members of the frame. So we have three members here. We have member AC, CD, and DB, right? We're going to apply slope deflection method at each member. For member AC, we are going to apply it at A and at C. So as you can see here, MAC, MCA. This is for member AC. Then we are going to apply for member BD, one at B, one at D. So we're going to have MBD, MDB. So this is member BD. And the last one is the horizontal element, which is CD. We're going to apply the slope deflection method at point C and at point D. So we are going to apply it at point C and point D. Okay. Now it is clear for us we are going to apply the slope deflection method like 6 times. We have 3 members and we are going to apply it 2 times at the ends of each column or each member. Okay, now the question is this: the main 3 unknowns for us, as we said, theta C, theta D, delta, they are going to be used as the main variables for the definition of all the moments here. So MAC equals to, this is from the slope deflection method, okay, the slope deflection equation, which is equation 16.19, I guess, okay. You can visit this in the previous video. So this is 2EI over H common times theta C, because we are talking, this is the far end here, and the 2 theta A, it is going to be 0 because our theta A equal to 0 and theta B equal to 0 because they are fixed. Then plus 3 times psi. This is psi that we have said before. It is going to be delta over H. So this is 3 times psi. Okay. And then plus the fixed end moment. The fixed end moment here. The fixed end moment AC. So we have the fixed end moment AC. This is fixed, and we have concentrated load. From the back cover of the textbook you can find and get the fixed end moment easily. Similar fashion, we're going to apply moment CA, which is going to be 2EI over H times 2 theta C, because it is, yes, 2 theta C is the near end, and the far end is theta A, it is 0, so you are not going to find theta A here, it's a 0, plus 3 times psi. In a similar fashion, you are going to apply the equations of the slope deflection for member BD and member CD. Okay, you are going to apply these two, the slope deflection at member BD and member CD. Okay, now let's go to the next step, which is the equilibrium equations. We need to put the equilibrium equations. We said we have, as I said before, 3 unknowns: theta C, theta D, and the deflection or the horizontal translation. So these are like 1, 2, 3 unknowns. This means that we require 3 equations for solving them. So we are going to apply the equilibrium equations. Okay, the equilibrium equations. So the equilibrium equations is telling us that the summation of moment at point C should be equal to 0. So we have moment from this side, which is, we call it moment from side AC. It is going to be moment CA. And the moment coming from the member CD, which is the moment CD, the summation of them should equal to 0. So MCA plus MCD equal to 0. And if we are applying this here on this point, which is point D, So the summation of the moment coming from member BD, which is M dB, and the moment coming from the member DC, which is M dC, mdB plus mdC should equal to 0. This is the second equation. This is the second equation. Okay, well, this is very nice. Now we want the third equation. The third equation is going to be, we call it the third equilibrium equation, commonly termed as the shear equation. Shear equation is based on the condition that the sum of all the horizontal forces acting on the free body of the entire frame must be 0. This means that all the forces applied on this system should equal to 0. We have the force, horizontal forces we are talking about, forces here. We have the shear at the bottom of this column, and we have the shear at the bottom of this column, right? So the third equation is going to be, if we're going to assume that summation of x equal to 0, taking this direction to be the positive, then P minus SAC minus SBD is going to be 0. You're going to ask me why this is minus. The answer is just we put it as an assumption. We're not sure whether it is right or wrong. We are going to be sure when we get whenever we get the real shear values. So this is only an assumption. We are assuming that if this is P, then it is commonly the forces at A is going to be in this direction, and the horizontal forces at B is going to be in this direction to counterbalance the external load. That's it. But this is only an assumption. Okay, this is only an assumption. We are going to verify it when we get the value of SAC and SBD. Okay, now let's go to the next part, which is how to get this SAC and SBD in terms of the moment. Remember that we need to express all our equations in terms of moment. So here in these two equations, the moments are the main aggregate of the equation. The main composition of the equations are the end moments of the column. But in this equation, actually, the components or the terms, they are not end moments, they are shear. So this is not good for us. We want to define this shear and this shear with end moments. So how we can do this? Then we're going to separate. We're going to take this column alone with a free body diagram, and we're going to take this column alone as a free body diagram, and then we can get SAC in terms of the moment, end moments, which is MAC and MCA. Let's see how this would happen. To express the third equation in terms of column end moments, we consider the equilibrium of the free bodies of the columns AC and BD. So this is AC and BD. When we take the free body diagram for member AC, we have the external moment, external force P, and we have the bottom column shear, which is SAC, and we are going to have the top column shear, which is SCA, and we are going to have the end bottom moment, which is MAC, and the top end moment, which is MCA. Okay, so we are going to take the moment around point C here for the member AC. So we're going to take the summation of moment at point C for the member AC only. That's the meaning of AC here. And the sign convention is going to be counterclockwise is positive. This is our sign convention. It should equal to 0. Then let's take the moment here at C. So it is going, we have a concentrated moment, which is MAC. It is counterclockwise, so MAC, positive, counterclockwise, remember. Minus, so here we are taking the moment here, minus SAC times H. SAC times H. Plus P times H over 2. P times H over 2, because it is counterclockwise, so it is positive. And then we have another moment here, which is MCA. It is, again, it is counterclockwise, so it is positive. MCA equal to 0. Right? So the summation of moments for moment at point C for the member AC is going to be 0. Rearrange this and let us put SAC in the left hand side and everything in the right hand side. Now everything in the right hand side is known for us. I mean not known, I mean that at least it is n moments. We have MAC, MCA, H it's known, P it is the external load which is known as well. We are going to do the same equation, equilibrium equation at point D. So take the moment at point D here, and counterclockwise is going to be positive, and it is going to be only for member BD. It should equal to 0. Taking the moment here, first of all we have MBD counterclockwise, which is positive, plus MDB, this is counterclockwise, it is positive. Again, this is for the sign convention. We are not sure what is the value exactly of this MBD and MDB. Okay, if it would be different than our assumption, then we are going to get it in the final calculation. Okay, and then the part which is I'm taking the moment here. So SDB does not make any moment. However, SBD is taking the moment, making the moment, right? SBD times the height. So SBD times the height. And this is, I assumed it in this direction. Then it is clockwise, so it is negative. Rearrange them and put SBD as a function of the end moments. MBD plus MDB over H. Okay, now let's go to the next slide and see how we are going to work. Now we are going to substitute with SAC and SBD with the moments. Okay, this is in the equation, this is equilibrium equation. Then we're going to put SAC with what we have done, MAC and MCV and so on. So we're going to put it here, and this one we're going to put it here. Then we're going to equate it to 0. This is where that we substituted and put it as I said in this equation. This is the equilibrium equation, and this is actually the same. It is the same equilibrium equation, just we substituted with SAC and SBD with these values here in terms of the moments and equate it to 0. Rearrange this equation and you are going to find that the equation is all the terms are end moments. This is what we are expecting, and the last term is PH over 2. It's known term for us, equating to 0. This is what we call it the third equation in terms of the end moments. Third equation in terms of the end moments. Okay, that's clear and good. Let's go to the next part, which is having some example and try to solve it based on what we have gained from the knowledge. So this example says, determine the member end moments and reactions. Remember that this is what I'm asking you now. It is not related to, no need to draw the bending moment and shear force and axial force. Only I want you to get the member end moments and reactions. These are the two things that I want you to get. Okay, as you can see here, this is the frame. We have A, C, D, B. Height is 7 meters, and this column is 5 meters. We have 3 meters each, and we have a concentrated load in the middle of member CD, which is 40 kilonewton. 40 kilonewton. Okay, now let's go and see what we are going to do. The first things is what is the degree of freedom, or what are the degrees of freedom? Okay, the degrees of freedom here is at C, it is free to rotate, so we have theta C. At D, it is free to rotate, so we have theta D. And there is translation, right, at the level of point of the member CD. So we have delta. So we have 1, 2, 3. 3 degrees of freedom, okay, which are theta C, theta D, and delta. Okay, so we have theta C, theta D, and delta. Okay. Okay, what are the other things that going to be? The other thing is going to be a kind of known for us. Xi is going to be known. As we said, it is tan. This psi is going to be delta over 7 meters, the height here. Or here, delta over the height. Okay, so it is known for us. And tan psi equal to psi because it's small angle. Okay. Okay, now let's go directly to fixed end moments. This is the first step for us. We have 3 members. This means that we are going to apply the slope deflection method at 3 members. This requires fixed end moments at the 3 members, at the ends of the 3 members. It is fortunate for us that AC, it is unloaded. So fixed end moments at A and C here, it is going to be 0, right? So this is why fixed end moments AC and CA 0. And fortunately also B, D and DB, they are going to be 0 because they are not loaded, right? So this means that also fixed end moments for BD equal to the fixed end moments of DB equal to 0. Okay, so this is very nice and very good, and it would make simplicity in our calculation. Then we are going to have CD. We need to calculate what is the fixed end moments at C and D. This is concentrated load at the middle, not at the middle, sorry. This is not at the middle. It's 3 meters and 4 meters here. So we are going to use this fixed end moment figure from the back cover of the book, which is PAB squared over L squared. So it is going to be like this: 40 times 3 times 4 to the power 2 over 7 squared. This is for CD. We're talking about this here. So it is going to be 39 something. So it is going to be counterclockwise, which is positive. And then DC, it is going to be with the DC is going to be with the other one. If we're going to, this is CD. So we have moments. If this is C, this is D. And we have moment here, and we have moment here. This moment is counterclockwise, which is positive here. And this moment, which is DC, it is going to be exactly negative. Okay, take care that the P, we have A here and B here. So this moment, which is moment MDC, different than the moment MCD. Here. So we found that it's 29 after the substitution of the equation. So based on this, we are going to, now this is the first step, we have the fixed end moments. What is the next step? It is the slope deflection equations. Okay, so now let's go to the slope deflection equation. Before that, we want the chord rotations, because the chord rotations actually, they are going to be in the slope deflection equations. So we need to determine them. They're easy, as we said. Psi AC, which is here, is going to be delta over the height. So it is delta over 7. But we put minus here. Why? Because it is clockwise. Similar here, this is the angle here, theta B D, it is clockwise. So it is negative. It's going to be delta over the height, which is 5 meters. Okay, what about the psi of the CD? Actually, it is going to be the same because here and here, the chord rotation with the horizontal is 0. So we have psi CD equal to 0. Okay, so that's very clear. I hope that it's very clear for all of you now to understand this and to go with the slope deflection equations, which is going to be in the next slide. Yes, the slope deflection equation is going to be applied at the three members, AC, BD, and CD. We're going to apply it 2 times at each end. So for example, for AC, we're going to apply it here at A and at C. So we have moment MAC and moment MCA. And then we are going to apply equation 16.19. From where this equation? It is from the next and from the previous video. Please revisit it and you are going to understand what I'm talking about. And here you are going to find that MAC equals to 2EI over H, which is 7, times theta C. It's the far end. It's the far end. Okay, so this is theta C. And there is 2 theta A. But theta A, as we said, theta A equal to 0. And also theta B equal to 0. Because it is fixed. So in this case, theta A and theta B, they are 0. Minus 3, which is the equation already we have. This is the equation. Times minus delta over 7, which is psi. This is psi. We're talking about psi AC. Rearrange it, you're going to find that this equation would take place for you, which is theta C and delta are the main unknowns. Repeat the same slope deflection method for CA. You are going to find this equation, unknowns, theta C, delta. Similar for all of the other members, theta D and delta, theta C, theta D, theta C, theta D. As you can see, all the moments are defined in terms of theta C, theta D, or delta. These are the main 3 unknowns, as I mentioned to you. These are the main 3 unknowns, as I have mentioned to you. Okay, so now all moments can be defined in terms of the thetas, theta C, theta D, and delta. These are the main 3 unknowns that we are searching for. Okay, now let's go to the next. What is the next? It is the equilibrium equations. We want to apply the equilibrium equation at point C and at point D, and we want to link between this moment and this moment at point C, and this moment and this moment at point D. Let's have a look on the next slide. So yes, this is what we were talking. So we have here point, this is point here, this point C. So we have moment here and moment here. This moment is MCA, and this is moment is MCD. The free body diagram is going to the summation of moment, okay, equal to 0 for point C. This means that MCA plus MCD equal to 0. And in similar fashion, for the other corner, which is going to be D, the moment here is going to be MDC, and the moment here is going to be MDB. The summation of them should be 0. MDB plus MDC should equal to 0. Okay, now this is the first equation. This is the second equation. Now let's go to the third equation. The third equation is going to be SAC plus SBD equal to 0. What is SAC and SBD? SBD, it is the shear at the bottom of column AC and the shear at the bottom of column BD. They should equal to 0 because we do not have any other external forces. Let's have a look on this. So actually we have vertical force, 40 kilonewton, but we do not have any horizontal external forces. And we have SAC here and SBD here. They are the only horizontal components that is going to be used. The only horizontal components that is going to be used. This means that SAC plus SBD equal to 0. Right? Now we want every one of them, SAC, as a function of the moments. How we can do this? Exactly, by the equilibrium equation, shear equilibrium equation. We are going to take the free body diagram of the columns independently. So column AC, as you can see, this is column AC, and this is column BD. In this column we have, at the bottom we have SAC, at the top we have SCA, right? Now let's say that we are going to take the moment, okay, at point C, for example. Okay, then you are going to find that SAC times 7 should equal to the summation of these two moments, which is MCA and MAC. This is what is giving here. So SAC times 7 equals to MAC plus MCA. So now we have the SAC as a function of the end moments of the column AC. In a similar fashion, we can apply this for SBD. So SBD, which is the, if we are going to take the moment here, so it is SBD times 5 should equal to the moment here MDB plus the moment here, which is MBD. This is the same as it is here. SBD times 5 equals to MBD plus MDB. Now we have the end columns shear in terms of the moment, right? That's clear. Then let's go to the next joint, the next slide, which is the substitution. Now, we said before, do you remember that SAC plus BD should equal to 0. So now SAC here, SBD to 0. Rearrange and you are going to find the third equation in the moment. This is the third equation. So MAC, MCB, MBD, MDB, it equal to 0, right? So we have, now this is the third equation. Now this one, if we going to put it in terms of theta C and theta D from the previous slides, now we have equation 1, equation 2, which are from the equilibrium equation, and equation 3 from the shear equation. Okay. Every moment here, MAC or MCA or something like this, they are given previously in terms of theta A and theta B, as we can see here. This. So it is theta C, sorry, and delta, and theta D and delta, and so on. So all of the moments here, they are in terms of these thetas. Theta C, theta D, and delta, right? Then we are going to substitute. Now it is the end almost of ours. So we are going to substitute in this equation here, this one and this one. These are the two equilibrium equations, which are here. So we have 1, 2, and 3, which are 1, 2, and 3. So we have 3 equations. We can work them simultaneously and solve them simultaneously. Then we can get theta C, theta D, and delta, as you can see it here. Okay, so these are the main equations and the main 3 equilibrium equations based on which we can obtain our unknowns, and then we can go to the next, which is the final step for us, that is putting all the values of the moment that we have on the diagram. Okay, actually it is enough for you to get these values, and then the reactions you are going to obtain it easily, because already if you know the moment, the end moments here, okay, then from the equilibrium of the joints you are going to have the shear on the beam, and then from this shear of the beam you can reflect it on the joint, and then reflect it on the other part of the joint, and then reflect it on the column, and then reflect it on the bottom of the column. Okay, this actually I think that you are familiar with it very much and you can do it alone. Okay, so now this is the end of the frames with side sway, and now we can put the support reaction, which is at the end. These are the support reaction at A, these are the support reaction at B, and these are the moments, internal moments. Okay, so this is the end of this example. I think you are ready now for in-class assignment. At this point you can stop the video and check what I'm going to highlight. Now this is the frame with the side sway in-class assignment. Very simple one. Only here we have support, which is roller, and the distance is 15 foot and 20 foot, and there is horizontal force 25K and distributed 2K per foot on the member BC. So let's assume this is how many, what are the degrees of freedom here? Actually this one is free to move in this direction. So we have a kind of what here? It is going to delta. So we have delta here. And this point, it is point B, it is free to rotate, right? It is going to rotate here. So this means that we have theta B also. So we have, this is 1, this is 2, right? So based on this, we have like 2 degrees of freedom here, and we can work them together. Okay, so 2 degrees of freedom. So I think that you can, as usual, you should stop here and try to solve it by yourself. And then this is the answer for it. So we're going to have the fixed end moments. We have fixed end moments AB, and BA is going to be 0 because we do not have any loading on this member. And then we have BC and we have CB. You can get it from 2WL squared over 12 from the back cover. The chord rotation here is going to be easy to be calculated. It's going to be delta over H, which is 20 here, and it is clockwise, so it is minus. Slope deflection, it is going to be applied at point or at the member AB and member BC. So we have MAB, we have MBA here, and we have MBC, and we have MCB. But MCB, fortunately, it is roller, so it is going to be 0. Then the equilibrium equation is going to be, yes, we have 2 like equilibrium equation. One from the application at point B, so we have the moment at point B, this is point B. So we have moment here and moment here. So we have moment B A plus the moment coming from this column, which is BC, should equal to 0. And the other equation is going to be from the shear equation. We are going to have the free body diagram of the column. We have only one column here. So from this column, we are going to say that the shear at the bottom of the column, which is SAB, okay, SAB of this should equal to the summation, or the summation of x should equal to f of x equal to 0. So SAB, which is going to be here, should equal to what? The external force here, which is 25. And then you can find that this would be the equation for you, that SAB from here, if you are going to take the moment at point B for the free body diagram, you're going to find that MAB plus MBA equals to 25, which is SAB times 20, which is the height. That's it. This is the second equation. So you have the first equation, second equation, and then you can solve and get theta B and delta easily. Okay. Okay, thank you very much for this, and I hope that you can follow what I have said in this video to solve the frames with SIDESWAY. Thank you, and see you in the next